On the video, good. Oh no, everybody can see my chats. Whoops. We're just gonna delete that out. Not that.
You're.
Now, okay, all right. So one of the suggestions I got was people wanted me to go over stuff and then do problems separately. I don't know if it was any of you that made that request or not.
I don't think it was
Okay, because one thing I was thinking about doing was kind of going over the slides that we kind of rushed over in the last two classes that were at the end.
Right.
Would you guys view that as beneficial?
Yes.
Okay, all right. By the way, something that I posted videos where I walk through all the pre-assignments, if you found those.
Yes.
I said it so you got an alert about that because I got my feedback from Dr. McCauley on yesterday. So I made those in response to the, oh my gosh, is that the passion tea?
Oh no, it's not hibiscus.
Yeah.
Good.
I'm really mad at Starbucks for getting rid of that, for getting rid of the hot tea.
Oh yeah, they don't have it that much.
Okay, so things we need to talk about. Okay, so enzyme regulation is one. Was there another one before that you guys want me to go over again in more depth?
I guess the main issue that I have was I know I understand the chymotrypsin mechanism and things like that. Yeah, I just think the issue that I have is understanding when the substrate comes in.
Yeah.
What happens? Because I get the steps and how the serine interacts and things like that with the nucleophile, but
okay. So what don't you? So okay. So if we have, or I guess so, there's the mechanism. I guess let me exit out of my. Now you know where I'm applying for jobs. Awesome. No, it's totally fine. It's not a secret. Okay. All right. So when we have the chymotrypsin mechanism, so we can just draw chymotrypsin out, and then there's chymotrypsin, and then we'll say here's the peptide. So that's the chymotrypsin, and that's the peptide. In solution, the peptide is kind of it'll bounce on, it'll bounce off, right? So we've got the K1, we've got the K-1. It's popping on, it's popping off. And then for however many times the peptide pops into the active site, one of them is going to be turned over and the reaction is going to turn over and you're going to get the reaction down to one half and then the other half leaves. And eventually water will come in there and then the substrate will leave and the enzyme will be back to normal.
So that part, the middle part that you just draw, that was the first tetrahedral carbon intermediate?
Yes. Yes. And I guess I wouldn't know how exactly to draw what the K2 would be for chymotrypsin, but I would imagine that the rate determining step could be some kind of, I would probably refer to that in conglomerate as the K-chem or the rate of the chemistry. I don't know what the rate determining step for chymotrypsin is. We're not concerned about that. But you're saying you're confused about what it binds.
I guess if when it binds and there's a bunch of types of bonding, and I just don't understand how you decide what, because there's so many different charges involved, especially with amino acids, because you have the negative charge and the C terminus, positive charge. How do you decide what binds to what part?
So you don't have to worry about that.
Okay.
So that's why we have extra crystallography. And so we're going to read a crystallography paper. I'm going to post it up right before spring break. We're actually going to read a crystallography paper, and you're going to see how they go through and they can identify certain amino acids that make contact with the drug.
Right.
But that's not something that you're going to have to pull out of your butt.
Right. You won't know exactly where.
If there are key features about the enzyme, I'll tell you. So it is good that you understand logically that there are a whole bunch of other interactions that are going on between the substrate. There are probably some interactions with the substrate other than what I showed you, right? But what you need to know for chymotrypsin is that there's a phenylalanine binding pocket or binding pocket where the aromatic can slip in. And we've talked about that in a different way when I was like, okay, let's propose what the binding pocket for the substrate for chymotrypsin would look like. So we've touched on that a little bit already. But the big thing here is understanding the features that I showed you is there's got to be something that's going to recognize part of the substrate, so that's the amino acid, and then you're going to have a part that's going to stabilize the tetrahedral carbon intermediate, specifically through hydrogen bonding with that oxyanion. So in this case, the chymotrypsin, we have a phenylalanine binding pocket, and then we have an oxyanion hull. And the oxyanion hull, like, it's still going to interact with the double bonded oxygen. It's just, it's going to interact, it's going to have a stronger effect on the negatively charged singly bound oxyanion.
Is there always an oxyanion hole when you bring the electron down, or is that just at first?
I would think it depends, and it would look different for the enzymes. Like you can have other functional groups or ions, whatever, fulfilling that role. No. So I would think so. I would think because chymotrypsin has specificity, I would imagine that pocket could exhibit a broad specificity towards aromatics. At least I would like to think so. That would make sense to me. I don't know that for a fact, but I would make an educated guess that it would.
Does that make sense, or am I just missing?
Yeah, so it makes absolute sense that it would be hydrophobic. Yes. So you could have two types of things going on. So you could have other aromatic rings that could form pi stacking interactions, but you could also have amino acids like valine, leucine, isoleucine, even alanine, just anything that's non-polar lining that pocket.
Right. So as long as you have, like, I guess this doesn't sound really weird, as long as you have some things that are lining the active site pockets that the substrate can bind to and form hydrogen bonds to stabilize it, then it'll work.
Yeah.
Okay.
And if we're showing you a mechanism in class, like we know that's the case. And if a protein binds to a ligand or an enzyme binds to a substrate, that's happening.
Like enzyme or not amino acids like that are present like that do that like in the active site. Are we supposed to like are we like should we know what kind of like peptides or like amino acids would then bind to that specific active site, or would we be told about that?
Oh,
so I just drew a general template.
Yes. So when you're doing this, just a general. So I very
like
purposely
like just like our group.
Yeah, that's totally fine. Okay. And I was gonna say when you see my key, it's pretty generic. Yeah.
Because it just said like
Right. Even if I tell you the amino acid that it recognizes, I'm really not that concerned about you drawing in that amino acid. That's on the record. Or if I change my mind later on, that's on the record. But I'm more concerned about you showing it splitting up the peptide bonds than I am about you drawing in the peptide. That makes sense.
So is that why, like, I guess when you have the binding, like if you have a really diverse like binding pocket with a lot of different amino acids, so that's why you can like have a ton of different substrates.
Yeah.
Okay.
So that's what makes, that's one of the things that would contribute to an enzyme having a broad specificity, or as we like to say in fancy pants protein world, if something is a promiscuous enzyme, yes, it probably would have a pocket that could maybe it's larger and that has different functional groups in it that could interact with different things. Yeah. So there's actually a whole field of enzyme evolution. And when I was in graduate school, I actually took a whole half of a class on this because the guy who was teaching it was in enzyme evolution at that time. So yeah, and it talked about how they just made rounds and rounds of random mutation to the active site of an enzyme that modified fatty acids. And over time, like the pocket shrunk. And so it could accommodate smaller and smaller. Yeah.
The bigger the pocket, the more, not like, I don't want to use the word functions, but like the more substrates it can interact with.
I don't know. Perhaps.
Kind of. Okay.
But I wouldn't worry so much about size. I think you were definitely on the right track when you were talking about size does matter to some extent. I wouldn't worry so much about thinking about whether or not. I like that you asked about the specificity, but that's not something I'm so much concerned about, is understanding that it's going to be complementary.
Okay, got it.
For this exam, yeah. But that's an insightful question. Well, I've got chymotrypsin up. Do we have any other questions about chymotrypsin?
You only use water as a nucleophile, and how much can you use other, like?
You tell me.
Um,
I was gonna say, let's take a look. Do you see something else acting as a nucleophile here? Yeah.
No, but for like the second portion of the
Oh.
transition. No, sorry, that was kind of a misleading question.
No. Okay, so what would happen? So serine can't act as a nucleophile because it's already attached.
Oh, yeah.
Yeah. So what else could you think? What else could act as a nucleophile?
Could you use
If it was small enough, yeah.
Okay.
And so that's one of the reasons why you're not going to see histidine attacking,
Right.
because it's just too darn big.
But like, it's normally just going to be water, right? Provide this nice.
Right. So if you were to have another amino acid go in, the
Right.
serine might leave, but then you would just be attached to another place.
Right.
And so your end goal isn't to keep yourself attached to the peptide, it's to have the peptide leave the active site.
As long as there's like electrons that, even if it like kind of messes up the stability of it, I guess.
So
That makes sense.
So again, there are, let's see, enzyme catalytic strategies. Is this the one? Oh no. Ah! Please stop. Oh my goodness. Why are you freaking out at me? I'm sorry, guys. Okay. I don't know what's going on, guys. Okay. All right. So apparently my PowerPoint hates me. Okay. So what were we asking before?
Honestly, I don't know.
I'm gonna shut down PowerPoint.
Yeah, very good. I think I was asking if you, as long as they like
Oh,
electrons.
okay. Yeah. So some amino acids are better nucleophiles than others,
Right.
though. So like, okay. So based off of what you've seen, what could be what? So serine is a good nucleophile, and why is serine a good nucleophile? Great. So when we're working with, let's find the in-class for enzyme mechanisms here, because I'm pretty sure that's the one where I have the table of nucleophiles. I'm pretty sure in that one. So serine's really good because it's because that one atom is like held further away. It's held that oxygen's held away from the backbone. It's separated by a carbon. And it doesn't have any, it's relatively sterically unhindered because it's just a single atom. And then you have a negative charge concentrated on one atom. So it really wants to like neutralize that charge. Okay. So again, oxygen, really good oxygen or like on a serine or just any free unhindered hydroxyl group. It's a really good. Turns out sulfhydryl groups, also good nucleophiles. Also carbanions as well as uncharged amine groups. So we've seen a hydroxide ion do a nucleophilic attack on the second half of chymotrypsin. Again, it says here imidazole can, but imidazole wouldn't be my go-to for predicting which one would be, what would be a nucleophile, because again, it's bulky and it's constrained in a ring. And so it could, but that's not something that I would instinctively be like, oh, let's make this attack. So like if I have, but I think it depends on the situation. So if I have a serine and I have a histidine, the serine's probably going to attack, not the histidine. But in histidine, what histidine's really good at is histidine is really good at playing a switch hitter for being an general acid-base catalysis. That's what histidine is. That's where histidine really shines. Yeah. Okay. Any other questions on common trypsin? Hey, Noah.
I have a question.
Okay. Yeah, sure.
This is going back to enzyme kinetics. I'm still
Fun.
confused on exactly what the KCAT means.
Oh, yeah.
What it is now, but
Sure. No, it's an excellent question. Okay, all right. So the rate of a reaction is dependent, or the velocity of a reaction is dependent on the concentration of the enzyme. So if you increase the concentration of enzyme, you're going to have more sites that can do chemistry. So you're going to have more product produced per minute, more substrate depleted per minute or per unit time, whatever. So the velocity of your reaction is going to increase with enzyme concentration, and it's going to increase linearly with enzyme concentration. Okay, so yes, and so when you get out of the range where you can accurately measure the slope, yes, eventually that would flatten off. But like oftentimes, if you look at a kinetic study where the authors are really rigorous about their work, they may show a plot where they show the velocity with enzyme concentration and show you that it's linear, so the range where you're using enzyme, where the enzyme concentration you're using is valid. Okay, but yes, so however, scientists, ideally, if you're in the lab and you're trying to replicate something from the literature, it's like if you're working with an enzyme, one of the first things you're going to do is you're going to make sure that what you see is within a reasonable amount of error of something that's been in the literature already. However, different labs use different buffers. Maybe you do it at different buffers. Maybe you're doing it at a different temperature. Also, yeah, there variations. Your people's hands just cause things to come out differently sometimes for whatever reason, or maybe you use a different instrument with a different error to quantify your enzyme concentration. So what you'll find is that depending on what your reaction looks like, you may have to use a different enzyme concentration, or depending on your assay especially. So like we see a difference in my lab if we use P32 or tritium or S35 as a tracer for our reactions. And so you may find that when you compare to someone else in another lab, or even somebody within your lab, you may have to use a slightly different enzyme concentration to get the best results. And so if you do a Vmax for your enzyme at 10 nanomolar enzyme, and the person in the literature gets their Vmax at a concentration of 80 nanomolar, your velocities aren't 1-to-1. You can't compare them accurately because you're using almost a 10-fold difference of enzyme, although it probably wouldn't be that big of a difference. But whatever. Either way, different people may use different concentrations from you. And so for that reason, that's one of the reasons where the KCAT comes in, because we want to get rid of any contribution from enzyme concentration. And so when we do the KCAT is equal to the Vmax over the total enzyme concentration. So we're literally dividing out the enzyme concentration. And so in theory, if for those two studies, once you divided out the 10 nanomolar for one study and the 20 or 40 or whatever nanomolar for the other study, your KCAT should come out to be roughly the same. They're not often going to be exactly the same, but they should be roughly the same. And so that's why we use KCAT in the lab, because you want to take out any kind of contribution from enzyme concentration.
So exactly what is the KCAT then showing? If it's the same for all of it?
The KCAT is the number of reactions that occur in a unit time. So either in a minute or in a second. So like the units are per second or per minute. And I'll tell you which I want to see in a problem. I think per second is standard, although I think the quiz was in per minute. but that tells you the number of reactions. So instead of nanomolar or nanomoles or micromoles or picomoles or whatever of product formed per unit time, you're figuring out how many reactions occur, how many reactions turn over per unit time. Yeah. How many times does it make the product? It depends.
That's one of the assumptions that we're making.
And it depends on the enzyme. But for most enzymes, yes. But if you have an enzyme that's diffusion limited, so where the chemistry is really, really fast, and the slow step is this enzyme finding the substrate, but that's something different. But to apply Michaelis-Menten kinetics, for our intents and purposes, we're saying that the chemistry is the slow step. But doesn't mean that's always the case, because again, we're simplifying. And when you simplify and you make assumptions, you have to simplify things for the sake of the math to work out. Okay, good question. And yeah, but while we're talking about it, do you guys understand the Kcat over the Km? I know we calculated it in class, but do you guys understand why the Kcat over Km is important? Yes, it's enzyme efficiency.
It's like the higher the number,
Great. Right, and so
that tells you like how well it's binding and how many reactions are happening. So it binds really well and it reacts really quickly.
So if it binds really well and reacts really quickly, you're going to have a really high enzyme efficiency.
How's that? Or is that you always want that?
You know, it really depends. But oftentimes, so I would say, so like the thing that I did in graduate school for my work was I studied whether or not enzymes become better or worse when you throw a bunch of crap in the test tube with them. And the idea being that the insides of cells are really crowded, enzymes exist instead of cells. So oftentimes some studies would do the Vmax, some would do the Kcat, but there's always the enzyme concentration so you could account for the changes. There's always the Km, and usually if they had the Kcat and the Km, you'd have the catalytic efficiency, so you could figure out how the overall efficiency of the enzyme would change.
The overall efficiency we consider.
Yep. So in this case, if we were to look at enzyme X, if we were to look at which was better in terms of K, which is faster, enzyme X is faster, enzyme Z is a tighter binder. And so, like for instance, having a low Km isn't necessarily the end all to be all, because if the enzyme binds a substrate too tightly, it may not be able to turn it into the product quite as well or quite as quickly. And so that's why we to account for those. I won't say that the two parameters are antagonistic, because that wouldn't be true, but they aren't necessarily working together. So you can have a change alter the efficiency, and when you see that with inhibitors, that just because one parameter is altered doesn't mean the other one will. And that's the same with the catalytic efficiency, and that's one of the reasons why we have to do the catalytic efficiency, because we want to take into account the strength of the interaction as well as the speed of the reaction. Okay. Did I answer your question?
Yes.
I like your sweater, by the way. It's super pretty. Okay, next. I can also point at slides and ramble. That's cool too. We can go over enzyme regulation again, but I'm also happy to answer questions as they pop up. Sure. Yeah, we can totally go over that. Okay. Enzyme kinetics. Okay. Yeah, and again, this is.
Because like I get that idea, I just
yeah, no.
conceptual part helps me.
Well, like it's a lot.
It's hard to picture.
enzyme kinetics is a lot. It's so much. Oh wow. Well, when I taught enzyme kinetics the first time, I actually went back to my kinetics notes from PChem and used those to help me, believe it or not.
It is kind of helpful because I'm like learning it. I mean,
Okay. All right, enzyme inhibition. Okay, we'll pull up this PowerPoint. Okay. Okay. All right, so you wanted to talk about mixed inhibition? Or was it uncompetitive? Uncompetitive. Okay. All right. So let's start, we're going to start with competitive. What competitive does is competitive is competing with the substrate to bind to the pocket. So a competitive, so this isn't an enzyme, it's an oxygen binding protein. But an analogous example to this would be thinking of carbon monoxide and oxygen binding to hemoglobin. So carbon monoxide literally unseats oxygen from the binding site. That's exactly what a competitive inhibitor does. Is the competitive inhibitor unseats, or it unseats, but it prevents the substrate from binding to the active site at all. Okay.
But that's not just like they don't even interact with each other at all. Like graphically, would they just not change?
Would what just not change?
Sure, because would it just stay with the y-intercept would be in the same location?
Yep.
Okay.
So they're gonna have the same y.
Right.
Okay. All right, they're gonna have the same y-intercept. Right. It's the slope's gonna be different because the km is changing. Okay. And this is one of the reasons why I'm like, I try to avoid just basically referring to the km as like the affinity, because it's more than the affinity, because the km is the constant. Because when you talk about so with inhibition, it's not that the km changes, is that you have a new km apparent, because the km is still inherent for the enzyme and the substrate. It's just inhibitors make the km look bigger or larger than it actually is. So if we have an enzyme that's being competitively inhibited, that means that some of the enzyme is being bound to the inhibitor instead of the substrate. And so in order for the enzyme to become half saturated, you're gonna have to kick off some of that inhibitor. And one of the ways you can kick out an inhibitor is by the brute force of increasing the concentration of substrate. So if we were to draw a graph, if we were to draw a Michaelis-Menten curve over here, this is VO, this is substrate, and we were to have, this is just enzyme. If we were to have enzyme plus inhibitor for a competitive inhibitor, the curve would shift to the right. The Vmax would stay about the same. What we would see is that to achieve 1/2 of Vmax, it would take a larger concentration of substrate to reach 1/2 Vmax than it would without the presence of inhibitor, because you have to overcome the inhibitor. It's the same thing for like why we do hyperbaric oxygen treatment for carbon monoxide, because you have to artificially jack up the oxygen concentration from what it is to get it to be there to be enough to outcompete. Because having an inhibitor with an inhibitor that likes the enzyme 200 or binding protein 200 times more than the actual substrate, I mean, that's you have to jack up your concentration to overcome that. Okay, so that's a competitive inhibitor. But I know you guys are nodding. You didn't specifically ask about the competitive inhibitors. I think you're feeling pretty confident about competitive inhibitors. But it really all just depends on how the inhibitor interacts with the enzyme or the enzyme substrate complex. Okay, so competitive inhibitors, we're increasing the Km, Vmax is about the same. And that makes sense, because once the substrate is bound. Once the substrate's there, the enzyme's fine. It's just whether or not you can catch the enzyme when it's not bound to the inhibitor. Okay. So the next type that we have is uncompetitive. And I always get so confused about uncompetitive and non-competitive. But uncompetitive, okay. So what uncompetitive does is instead competitive, which binds to the enzyme alone, the uncompetitive inhibitor binds to the enzyme substrate complex. So once the substrate hops on into its little substrate, So once the enzyme, the substrate hops on to its little substrate product, and it's like, yeah, pocket. It's like, yeah, the inhibitor then is like, ooh, once the substrate binds, a pocket will open up for the inhibitor, and the inhibitor then will jump into that pocket. And once the inhibitor binds, it temporarily takes, depending on whether or not it's reversible or irreversible, which the vast majority of the time these guys are reversible. Not irreversible, reversible. They can pop off and pop on. Okay, all right. Okay. They can bind. Then what happens is once you have the substrate and the uncompetitive inhibitor bind, it temporarily knocks the enzyme substrate complex out of commission. Yeah, but temporarily knocks the enzyme substrate out of commission, and it can't do chemistry anymore because it's taken out of commission. So if we were to look at the effect on kinetics, what's happening is the Km is decreasing. So that seems a little bit counterintuitive because you would think an inhibitor would be detrimental to the enzyme, and so you would expect that it would have like a detrimental effect on the Km. But it doesn't. That's because when you take the enzyme substrate complex out of commission, you're lowering the number of enzyme sites that are available to do chemistry. Exactly. Yes. Because you're literally knocking out active complexes, it's going to take less substrate to saturate the enzyme complex, the enzyme substrate complex, or the enzymes alone that you have there. But okay, but then also the Vmax, okay, yeah. So, but then also if you have a smaller enzyme concentration, so you have fewer enzyme sites available to do chemistry, what did we learn about enzyme concentration in Vmax? Oh, okay, alrighty. Okay, I was gonna say I asked you because you asked that insightful question. If we look back, it's okay, Colin. It's okay. Okay, what happens to the velocity as we increase enzyme concentration? Exactly. So when you knock out the enzyme substrate complex, you're lowering the concentration of enzymes. So effectively, the apparent concentration of enzyme, not the actual concentration of enzyme, the apparent concentration of enzyme. So that causes you to lower the Km because less sites are available. Mm-hmm. The other part of that is that the reaction rate is dependent on the concentration of the enzyme or the enzyme substrate binding sites that are available. So if you're knocking out some of the enzyme, you're decreasing the number of sites, so you're going to decrease the Vmax because you're going to decrease the ability of the rate at which the enzyme can do the reaction. So those two go hand in hand. And competitive, and the way I like to keep it straight is that competitive binds to the same pocket. It's competing with the substrate to bind to the active site. Uncompetitive inhibitor is binding somewhere other than the active site, but it's changing the shape of the enzyme so it can't do chemistry. The last is mixed, because mixed, and like again, you said mixed or is it uncompetitive, but we're just going to say mixed. And the reason why we call it mixed is because, well, the effects are mixed. It can either bind to the enzyme like a competitive inhibitor, or it can bind to the ES like the uncompetitive inhibitor. And so the result of this is that no matter what, the Vmax is going to decrease. However, the Km can increase or it can decrease depending. Because if with competitive, we saw it increase, with uncompetitive, we saw it decrease. And then Vmax, if you're screwing with the enzyme, if you're screwing with the enzyme, either way, if you're lowering that concentration, the Vmax is going to decrease. And so what this looks like, okay, and so if we were to draw these two as substrate saturation, so we saw with the substrate saturation curve, actually, no, we'll go and we'll look back. So if we look at the substrate saturation, or the Lineweaver-Burke plots for these two, the Lineweaver-Burke plot for uncompetitive inhibition is those very distinct parallel lines. And that's because the Vmax and the Km are going to decrease proportional to the concentration of the inhibitor. So the slope isn't going to change because the Km and the Vmax are going to be affected proportionally. It's just going to scoot on up the y-axis.
This is uncompetitive.
Yes. And then non-competitive, the non-competitive is going to look more like the competitive because the Vmax is going to decrease, but the Km may increase or decrease. And so the result of this is that the lines are going to intersect, but they're not going to intersect on the y-axis because your Vmax is decreasing. But the slope is going to change because the Km may increase, the Vmax may decrease, whatever, but they're not necessarily going to change proportionally. Okay. Alrighty. Looks like we're starting to fill up now. Hopefully we won't exceed the max of everything. Okay. All right. Now, if we were to draw these as substrate saturation curves, okay, so we've got competitive. So if we were to have non-competitive, what happens to the Km for non-competitive? Or uncompetitive. What happens for uncompetitive? Okay, so the Km decreases, and then what about the Vmax? Okay, so where would my plateau be relative to the plateau for the enzyme and the competitive inhibitor? It would be lower. Yep. And so then where should I draw my curve? Should I draw it to the left or to the right of the enzyme and with no inhibitor? That's right. So we would draw it to the left. So if we were to find where we're meeting half max, it would be at a lower concentration than either enzyme alone or enzyme and then inhibitor. And then the last one to think about is the mixed, good old mixed. Okay, so the mixed, what's happening to the Vmax? Okay, so it's going to be decreasing no matter what. So like with the enzyme and the blah, blah, blah. Okay, it's still going to be lower, but where things get a little different is it can be to the left or it can be to the right.
And so, like, the active site,
Logically, that makes sense to me. Logically, it makes sense that that could be the case.
but we just need to know that it can be.
Yeah. Usually, like the very cut and dry examples are competitive and uncompetitive, and then mixed is kind of like a. I mean, it's there and you should be able to identify it, but usually that means you have to do more work to figure out what's going on. So, but no, it's a thing. No, it can happen, but it's not necessarily. It's not definitely not nearly as clear cut as the other alternatives. Okay. All right. Welcome. What should we talk about next? All right. Do you guys have any other questions? Do you have any topics that you'd like me to really quick run through or touch on before you dash out? Okay, Noah, how long are you sticking around for? Okay, you don't know. Okay, but Caroline, you have to leave.
Yeah.
You think you're good? Okay.
I just know. For part of it, don't we write on
would say write down on
Okay,
nicer
sorry.
paper. No, it's totally fine, but
It's
You
yellow.
could-
I know,
you
I know,
could-
not yellow.
you
That
could.
was my fault.
I wouldn't take off points, but I do want to make it the easiest possible for me to see.
Yeah, definitely. Okay, I'll do
I was gonna say,
Yeah,
you
yeah.
know, I'll say what my graduate advisor would say. He would say, the less confused I am, the better mood I'm in, and the friendlier, greater I'll be. Okay. Of course. All right. Okay, so I was gonna say around 7, I was gonna take a quick break and run and heat up some dinner for myself. Does anybody have to leave like very soon after 7? That this would be a problem. Okay. All right. So new group of students. Okay. So what we've been doing up until now is, except for Sean, is we've just been 2 out of 3. Wait, what? There's what? A rogue what? Oh, it wasn't me. I'm a never smoker. Okay. Goodness. So what we've been doing up until now is we've been doing like the question and answer format. I don't know if you guys want to continue with that, or if there's a topic that you'd like me to just kind of talk broadly upon. Like one of the things I was going to suggest is, do you want me to run over like regulation again, those last couple slides? Or is there anything particular you would like me to just talk about? Mhm.
The enzyme, like, out, like,
So the way that it really depends for you, because you could say either the inhibitor decreases the Km, or you could say the Km of the uninhibited enzyme is larger than the Km of the inhibited enzyme. Either's fine. I think in terms of, let's talk about the inhibited enzyme relative to the uninhibited enzyme. But I mean, either's correct. I'm not going to put a value judgment on how you think about things, as long as it's clear. If I get confused and I'm tired when I'm grading, I might get confused and you might have to point it out and I'll correct it. But usually I try to be pretty liberal-minded towards alternate modes of thinking. And it was a little bit confusing because, yeah, the book has it set up like that, which I personally find I find it's confusing. But some people think like that. Clearly the people that wrote the book think like that. And they're smart biochemistry education people. So, yeah. Okay. Yep, no. Oh, yeah. Sure. Yeah, okay, sure, we can go over that. We can go over that generally speaking, not using data from the exam. Okay, all right, I'm gonna stop projecting really quick so I don't just project answers on the board. Okay, all right. Actually, let me really quick. I can pull up data from last semester. We can do that. Let's see, quiz. So how are y'all doing tonight? Oh, goodness. Okay. Yeah, tell me about it. Tell me about it. I was gonna have like 2 hours before this to get a bunch of crap done, and then I had a radioactivity scare, and well, that didn't happen. Okay, enter the password 4774. Yeah. I finally gotten past the point in my life where I was having nightmares about spreading radioactivity everywhere, and then that happens. Okay. All right. So these are some enzyme data for an enzyme. So I used DHFR last semester too, different numbers, right? But what I did, yes, this is from last term. But what I did is I said, okay, here's the enzyme in the presence of, here's the velocity as a function of DHF. And so if we were to make just a Michaelis-Menten plot, we would insert, and we would see that we get a substrate saturation curve. So a Lineweaver-Burke plot is just a fancy name. It's named, I guess, after the scientists who applied it to enzymes. But back in the day, so Michaelis and Menten made their discovery back in like 1912. So in 1912, they didn't have computers. So they see this curve plot and they're probably like, what the F? And so scientists came up with a way that you could fit these data without having to get into like hyperbolic curve fitting. Because like you can hyperbolic curve fit in Excel, it's just really roundabout. Like I don't even know how to do it. I look at the instructions and I'm like, no, I'll just use Sigma plot instead. So it turns out that there's an old trick. That you can use to make curve data linear. And that's called, called making a double reciprocal plot. And so the reciprocal of something is simply taking the inverse or 1 over something. And so if we have a double reciprocal, that means you're making a plot of the inverse of both the x and the y-axis. And so you could think of making a double reciprocal plot as magically linearizing your data. All right? And so what we do here is we would say, okay, literally, let's just take 1 over our substrate concentration. We would take 1 over the initial velocity. All right. And then I'm a dummy, not a dummy. I shouldn't talk about myself like that. But I still haven't figured out how to like make plots from numbers that aren't right next to each other. I know there's a way, but I always get confused. Okay, so create a plot these out. All right, only paste the values. So this is 1 over substrate, and then 1 over initial velocity. And so you can make, they will insert a chart, and then voila, you have a line. So the example that we had in class was not a line. It was like very obviously not a line. It was very obvious that if you took out the furthest out point, which is the smallest velocity, you would get a beautiful line. And I did that intentionally because I wanted to prove a point. They say, in terms of data for experiments, garbage in, garbage out. And if you do a Lineweaver-Burke plot, that's a very clear case of if you put garbage in, you're going to get garbage out. That line, because the linear fit unevenly like weights the far out to the right end of the fit. And so whereas if you had a direct fit, if this number was a little bit off, especially if you've done a 0 and gotten a baseline, it would become like you wouldn't feel it as much. But when it's at the end of a line, if it's off, and very oftentimes if there's going to be a data point that's going to be off, it's going to be this one, because that's going to be the value that the measurement that's closest to the noise, so it would have the largest error associated with. That can really mess with your numbers. Now, most of the time, if you have decently good hands, your data are going to be fine, and your Lineweaver-Burke plot's going to be okay. And like if you fit it, you get a really good R squared. So like if we take these data, if we fit them, okay, we display our equation, we display our R squared. We've got an R squared where we have 3 9s in it. And if we look at the line, it goes through all of the points. So it's probably a fairly good fit. So this is a set of data where the people who collected the data got good data. So in this case, the Lineweaver-Burke probably okay. And most of the times it is. Yes.
I'm going through this example with the
Yeah.
and like R squared is just like 0.95.
Mm-hmm.
So it looks like I'm really far off point on this plot. It's just
So I made the class go through and calculate the values, and then you'd see that they'd be very different. Specifically, I think the Vmax, the Km, I think was like an order of magnitude lower than it should have been, and the Kmax was like 35 versus 50. And you were given the equation, so you were supposed to see that like it was off. And you could tell even off if you like if you estimated the Vmax and the Km from the curve plot that you drew out, or I think I included a curved plot, like you'd be able to see that something was going on in the linear transformation. But this is a case, these data that I pulled up, this is a case where it survives the linear transformation, and so there's not really a problem there, but there was definitely a problem. And so in that case, I see you. There, in the case of the other data, I would say you probably could exclude it because it's close to the noise, or you could rerun a set of experiments and don't include that one, or you could try to use a concentration that was a low concentration that was higher than that was a little bit further away from the noise. Yes, Paige. This one, yeah, this is fine. So it's not an outlier because it's on the line. Yeah, no. So the fact that it's far out doesn't make it an outlier. It's the fact that if the line between these points is here, if your point was up there or down there, that's what would make it an outlier. Because it was like the first 8 points fit on a line and the last one doesn't. And then you get a fit that's really shitty. Okay, so let's see. I think I have the data from class. I'm pretty sure I have a filled in Excel sheet that I can pull up. Okay, let's see, enzyme kinetics. Yeah, there we go. Oh, no, okay. Okay, yeah, no, okay. That was one I posted for you guys to do, and then this is the completed data set. Okay. All right, so the thing that makes this an outlier, I would even hesitate to call it an outlier, because I think it's just really a flawed data point, because it's probably flawed in the way the data was collected. Although you could always repeat it and see if it happens again, and that's how you would know if it was an outlier. But the fact, again, that it isn't an outlier isn't so much that it's all the way out here. It's the fact that if we were to just so if we were to just graph, insert, if you were to just graph these points alone, first of all, the R squared goes up.
Yeah.
And then
the one right below R squared.
Yep, so you could keep subtracting. And so like when I generated this data set, I made an equation. I screwed with the points a little bit, so it wouldn't be a perfect line, right? Okay, yeah. And then I added in that one to be an outlier because I wanted to show what happens when you have an error-prone data point go wrong. Because sometimes when you're measuring these enzymatic assays, you're looking for a slope, you're looking for a change in concentration and time. If you get a really small substrate concentration, it could be near the background. So that's actually a big problem that I had in my grad work, is because my solutions are really viscous, and so there'd be a really big background fluctuation. So I had to make sure my slope was big enough that it could be significant over the contribution from the background, and that was not fun. So yeah, anyway, yes. Here we go. Okay, so yeah, so once you get rid of that point, like the slope of the line changes dramatically. And if you look at this line for the whole data set, it only goes through 2 points. It goes through the last point, and it doesn't even go through the last point. The only point it really goes through is that one. And so even though it has an R squared value above 0.9, like, yeah, it's only going through 2 points. You can have a line for like 10 points if it only goes through 2 points. Something's going on there. And so again, this is an example of where if it was a linear plot, or if it was like a curved plot, these points would be weighted a lot more heavily than that one. Because it's a line and it's a linear fit, it's going to want to go through the furthest out point. I would say supply as much information as you feel is necessary, right? So what do you need to be able to provide me with to tell me about the mechanism of enzyme inhibition or how the KM and the Vmax are affected?
So how do you go about that?
So the KM and the Vmax, there's a slide for that. And I feel like that's where I want to be careful because I don't want to say like too terribly much. Also, I know it's hard because you weren't in class. But the way that you would go about, what I will say is that it's a linear fit for the Lineweaver-Burke plot. And so the equation for the Lineweaver-Burke plot is linear. So if we were to actually write this out, let me go into my little thing here now. So for the Lineweaver-Burke, we have 1 over V naught, and then we have 1 over substrate. Okay? And so if we have it, it's in a line, it's in good agreement, whatever. So if we have the form y equals mx plus b, our y, what's our y? So if we were to look at this graph, what's on our y-axis? Right. So our y is going to be 1 over v naught. What's our slope equal to? Oh, let's see. Okay. Actually, no. So the slope, I'll go ahead and say that. So what's our x? Right? Our x is 1 over substrate. So our slope is going to be equal to, I think it's Kn over Vmax. And then our b is equal to 1. So the point at which our vine is going to cross over the y-axis is equal to 1 over the Vmax. So there we go, 1 over Vmax. So you can figure out if you solve for b. Okay, I'm going to let you walk yourself through this. How would you solve without confirming or denying? How would you solve for b? If this was just a line, how would you solve for b? So let's say we have so let's go to this. Let's go to our example from class. Yeah, we can do our example from class. That's fair game. So if we have our equation for our line, and let's do what we did in class, and we say we have this equation here. So let's see, y equals 0.0018. Plus 0.0282. Okay. All right. So what's going to be our low-hanging fruit here to solve for, Noah? What can we solve for relatively easily? Okay. All right. So if we have our y-intercept is equal to 0.2082, and our y-intercept is equal to what? In terms of the kinetic parameters. So our b is equal to 1 over Vmax. Okay? So if we have the number for our b, and that's equal to 1 over Vmax, how would we solve for Vmax? So yep. And that should turn out to be, I think, about 35, whatever the units are. Can't remember what the units are. Yeah. Yeah. And that's one of the reasons why we do this, because it's that simple. That's one of the reasons why Lineweaver-Burke is taught a lot in class, is because it's really easy to solve, and then it's particularly good for representing modes of illustrating modes of inhibition. It's particularly strong for that. There we go. Okay, we're going to be difficult. We're going to crap out. All right, of course. There we go. Are you serious? We're going to start. Okay, let's start sharing. Start. Okay, all right, apparently. Okay, all right, let's start. Okay, there we go. All right, so if we can solve, for B. So then once we have B, we can solve, we can solve for V max. So once we have V max, we can solve for Km. And so we know that our N, what's our M equal to, Noah? Yep, so 0.0018. So what is our slope equal to in a Lineweaver-Burke plot? That's right. So 0 has our Km over V max. Okay, so we have one number and we have two variables on the right-hand side of the equation. We simplify that anymore. Okay, yep, exactly. So we can do 0.0018, and certainly there are units there, which I'm being a bad professor and neglecting, times the value for V max, which in this case, I think is 35. And I think we should, I can't remember, it's a really low number. I want to say it's like 0.05 or something like that. So whatever 0.00, let's see. Pardon? Yeah. So 0.00018 times 35, yeah, about 0.06. So it's a lot lower. It's a lot lower than what we would have predicted based on the data that are in the handout and what would have been what would have been the corresponding hyperbolic fit. So okay, so if we look, so we can go to the handout. All right, let's go to the handout here. Where is it? Where is it? Okay, enzyme kinetics in class. Okay. Okay. All right. Open this guy up. Okay. So if we look at the data, you should be able to predict, based off this plot, what would you predict the Vmax is? So that's one way. So yeah, so if you have the plot, you could estimate it based off what the highest number for the V naught is. But also, if you just have a plot, not a table, you should be able to predict it by where it levels off and flattens out. Yeah. So it should be about 50. So if we get about 50, and then we look at our fit from our Lineweaver-Burke, and we're getting 35 micromolar per second, you know your fit is off because the fit from the Lineweaver-Burke is not matching what you predict the Vmax to be just from a cursory glance at the data. If you were to fit this and you were to get a Vmax of 45, it would be like, or even like a Vmax of like 51 or something like that. If it was to be around 50, it'd be okay. But because it's like, it's like 20% lower than what you would have predicted just from looking at the graph. And that should be a red flag. Okay. Yeah, and so you could also, you could totally predict the KM too. And so if we were to look at that table, what would we predict our KM to be? You guys are also welcome. I was going to say Roshan, Rupert, Cage, you're also welcome to contribute or to chime in. Pardon? Yeah, we would expect it to be about 0.25. So our V max is around 49 or 50. We go to 1/2 of that's around 25. And so that would correspond with a substrate concentration of around 0.25 millimolar for being a Km.
Oh, okay.
And so if from our Langer-Burke we're getting a Km of 0.06, we're almost an order of magnitude lower than what we would have predicted, which is a big difference. If it was like 0.4 or even 0.1, it'd kind of be like, eh. But if it's like almost an order of magnitude different, like more than like 5% different from what you would have predicted from the data, or even just from looking at a cursory glance, there's a problem. There's a problem with the Langer-Burke. And in this case, you saw even just from looking at the line, there was a problem there. But just because there was a problem in our example doesn't mean that there's always going to be a problem with the Langer-Burke. And most of the time, I found that when I would do examples for students in class, at the very beginning, I would make a data set and be really disappointed when the Langer-Burke was right. You really have to kind of screw with that first data point. It has to be really messy for it to not work. But if it's not accurate, it's a problem. First, you have a little more wiggle room with the points, say in the plateau area. No, it's totally cool. So I was gonna say, I know Roshan was here for inhibitors. Paige and Rupert, were you guys here for inhibitors? Yeah. Okay, we'll go over inhibitors again. That's fine by me. I could talk about inhibitors forever. Okay, so what inhibitors do? Okay, so we'll go ahead and we will go through the 3 classes. Those of you who are watching at home, you can just fast forward through this unless you want to see it again. Okay, so competitive inhibition. The analogous thing that helps me compartmentalize competitive inhibition is actually thinking about a binding protein rather than an enzyme. So what's the difference between a binding protein and an enzyme? What's the main difference? I was going to say, I know we talked about a page, but I don't want to put you on the spot. So both a binding protein and an enzyme are going to bind to their substrate or ligand. The difference is that the enzyme is going to help turn the substrate into something else. So that's why we give the ligand for an enzyme a special name. We call it a substrate because it's going to be turned into something else. Now, that reaction would happen on its own. It would just be really, really slow. So like that's one of the reasons why thankfully our proteins don't spontaneously break down, is they will happen. It'll just take thousands of years on their own. Enzymes just lower the activation barriers, so it takes a lot less time. Okay, so competitive inhibition. I like to think of hemoglobin, and I like to think of hemoglobin for oxygen versus carbon monoxide. So carbon monoxide, homotropic allosteric modulator, and it's homotropic because it literally competes with oxygen to bind to the heme on hemoglobin. In fact, carbon monoxide is a better ligand than oxygen, and it binds 200 times more strongly to hemoglobin than oxygen does, which is a problem. And so what happens then? So a competitive inhibitor for an enzyme, like carbon monoxide, is going to compete with the substrate to bind to the active site. So it's going to bind in the same place in a very similar way. And it's a pretty good guess that it's going to look like the transition state, because good enzyme inhibitors look like the transition state and they just lock the enzyme there. The enzyme is like enticed into binding it because it looks like the transition state. And oh, that hydroxyl group can fit in my oxyanion hole, and that phenylalanine can go in the phenylalanine pocket. But then when the enzyme tries to attack it, it either gets stuck or it just can't do anything. And eventually it'll spit out the inhibitor, but it really just depends on how well those interactions are optimized, because oftentimes inhibitors are stronger binders than the substrate, which makes sense because the substrate, you don't want to bind too strongly because you don't want to have too small of a Km. You don't want a Km that's so small that it won't react on it. Okay, but competitive inhibition, okay, so we're taking the enzyme binds the inhibitor instead of the substrate. And so then what happens is when the enzyme binds the substrate, if you want the substrate to bind to the enzyme and then reach 1/2 of Vmax, you're going to have to add more substrate to make the substrate concentration look bigger to achieve the same velocity that you would achieve when there's no inhibitor. Okay, so if we look at our plot over here, so if we were to look at the curve of the substrate saturation curve for the enzyme in the presence of a competitive inhibitor, instead of on its own, this curve would shift over to the right, because in order for us to achieve 1/2 Vmax in the presence of the enzyme and the competitive inhibitor compared to no enzyme, it would take more enzyme to saturate 1/2 of those sites and then lead to 1/2 of the Vmax. And so it's kind of like the same principle for hyperbaric oxygen treatment for carbon monoxide poisoning, is if you have a high enough concentration of oxygen, enough will bind that it can unseat some of that carbon monoxide, but you're going to have to make more. You're going to literally have to try to flood the enzyme, the hemoglobin with oxygen to get it to kick off oxygen. It's the same thing with a competitive inhibitor. In order for your substrate to outcompete the inhibitor to bind to the enzyme pocket, you're going to have to jack up your concentration of substrate. And so that's kind of how I think of it. So that's one of the reasons why I don't like to talk about the Km as just the affinity constant, just talking about the affinity, because it's not really, because that does you a disservice to think about when you're thinking about how inhibitors affect the Km and make a new Km apparent, is because you're thinking of, okay, how much substrate do I have to have around to reach 1/2 Vmax compared to the substrate that I need when there's no inhibitor around. Now, so everything with competitive inhibitor has to do with substrate binding. Once the substrate binds, nothing changes, because you don't have to worry about the competitive inhibitor like messing with the structure of the enzyme. It's going to pop off, the substrate will go in, and then chemistry will proceed as normal. So for that reason, we would see the Vmax would not be changed. So the top of the curve for the enzyme in the presence of a competitive inhibitor is going to be the same height as just the enzyme by itself. It's just the Km, the curve is going to be shifted to the right because the Km is going to be increased, because it's going to take more substrate to reach 1/2 Vmax than it would if you just had the substrate and the enzyme alone. And if we were to look at this in terms of the Lineweaver-Burke plot, again, this is where Lineweaver-Burke plots are really valuable, is because they're really good at illustrating inhibition. Now, if you're talking about what an inhibitor does, I don't want you to say, oh, the Lineweaver-Burke plot, they intersect on the y-axis. You'll get like a point if you do that, because you have to explain it in terms of what happens to the Km and the Vmax. And I feel like I've been pretty upfront about the fact that you need to talk about it in terms of the Km and the Vmax. And so if we're going to look at the effects on kinetics, we're going to intersect, we're going to intersect on the y-axis because the Vmax is changing. Because the y-intercept is equal to 1 over to Vmax. So if Vmax doesn't change, your y-axis isn't going to change. Your y-intercept isn't going to change. So all the lines are going to intersect at the y-axis. However, the Km changes and the Km is going to increase. So if the Km increases, our slope is equal to Km over Vmax. The coefficient of your slope is going to get bigger with increasing inhibitor. So the slope is going to become bigger, or you're going to see the line become sloped more steeply than without the enzyme. And so the slope of the line is going to change, is going to increase, but the intercept isn't going to change. Okay. Any questions on competitive inhibition? Yeah, Rupert. Okay, so I'm not worried about alpha, but alpha, yeah, I'm not really concerned about that. But alpha has to do with when you increase the concentration Okay. So the reason why people do alpha sometimes, I don't do it because I think it's more confusing for beginners. But the reason why it's used is it's to hit home the point that the KM isn't actually changing. The KM is an inherent property of the enzyme substrate pair. It only appears, basically what's happening is when you get the new KM or the KM apparent, you're basically just multiplying the KM by a constant. And so this is showing, so you can either do alpha times the KM or you can do KM apparent. But this is just to show you that when you get the new slope, it's not that there's a new KM, it's just that you're multiplying the KM by a constant to make it appear bigger in magnitude. And that's what alpha means. All right. And then Vmax, there's no alpha there because Vmax doesn't change in the presence of a competitive inhibitor. So next, you ready, Noah, for uncompetitive? Okay. All right, so uncompetitive. So competitive competes with the substrate to bind to the enzyme alone. An uncompetitive inhibitor is only going to bind to the enzyme after the substrate binds. So it's going to preferentially bind the enzyme substrate complex. So visually, we have an enzyme with two pockets. All right, so we have a pocket for the substrate. We have a pocket for the uncompetitive inhibitor. So the substrate goes in and it binds into its little hexagon pocket. Then once the substrate is bound, the inhibitor can then go in and bind too. But for an uncompetitive inhibitor, what happens is once the inhibitor binds to the substrate, it makes some kind of conformational change happen to the enzyme that the enzyme can't do chemistry anymore. So it's effectively taking the enzyme substrate complex out of solution. All right. And so then what happens, what's the result of this is if you're making the enzyme inactive by binding the enzyme substrate complex and you're taking some population of the enzyme out of solution, you're going to effectively lower the concentration of enzyme that's available, or you're going to lower the physical number of sites that are open to do chemistry. And so when we do that, we're going to have these effects on the kinetics. So the Km is going to decrease. And so we think about the Km is the amount of substrate that we need to reach half Vmax. If you have fewer enzyme sites available for the substrate to bind to, then it's going to take less substrate to reach half Vmax. So if you have fewer enzyme sites available, it's going to take fewer molecules of substrate to reach half Vmax, and so the Km will go down. This page. Sure.
So are you
Yeah.
if the inhibitor wasn't there, it would be another
No. Nope. If the inhibitor didn't bind, there would be nothing. The reaction would just proceed as normal to EP, E plus P. Oh, so that can't do anything. So I like to think of the uncompetitive inhibitor as the uncompetitive inhibitor knocking the enzyme out of commission. Mm-hmm. Yep. Yep. So once the substrate binds, and then the inhibitor is like, nope. And so then it can't turn over. It's kind of temporarily stuck until the inhibitor pops off. But you're literally removing ES complex from the equation. Yes, Rashawn. It depends. It depends on the strength of the interaction. But in theory, with a competitive inhibitor, it's just taking the place of the enzyme. It's not physically altering the conformation of the enzyme. And so that would also have an effect too. Yes. Yes, it doesn't change the conformation of the enzyme. At least it shouldn't. This is where hemoglobin is an imperfect model. Another reason why it's an imperfect model, other than the fact it's not actually an enzyme, but because carbon monoxide locks it into the R. Oh, fun. Fun times of hemoglobin.
So you said for but
it also affects so what we see with uncompetitive is that because because we distort the active site, we make it inactive, you're lowering the effective concentration of the enzyme that's available to do chemistry. And so the effects of what would happen to the enzyme are analogous to what would happen if you were to compare an enzyme. Actually, that's not 100% true. That's not 100% true because the Km is independent of the substrate concentration. But if you were to have fewer bindings, it would be if you were to have fewer binding sites available for the enzyme, it would make sense that it would take less substrate to saturate the enzyme. So it would appear that your Km would be decreasing. Km's not actually decreasing because the Km is an inherent property, but you're manipulating the enzyme so the Km appears lower. The other side of that would be if you were decreasing the amount of enzyme sites that are available to do chemistry. If we remember, we talked about this when we were talking about the Km versus or the Kcat versus the Vmax. One of the reasons why we use the Kcat instead of the Vmax is because the velocity of a reaction increases linearly with enzyme concentration. Because if you have more enzyme, you have more active sites available to do chemistry, and therefore you're going to have a larger velocity. You're going to be able to turn over more substrate into product. And so if it looks like we're decreasing the concentration of our substrate, we're going to have fewer sites available to do chemistry then. It's going to look like our Vmax is going to decrease, and we're going to have a lower apparent Vmax than the uninhibited enzyme. And so you can see here that we see, it's the alpha prime there, but yes. So, and then what happens is both the Km and the Vmax are going to decrease. And so because both of them are decreasing, and they're going to be decreasing in a proportional manner, we're going to see the y-intercept get larger in magnitude on this plot because the Vmax is going to decrease. So 1 over a smaller number would give a bigger intercept value for the intercept. And then also because the Km is decreasing, or because both the Km and the Vmax are decreasing, and they're going to be decreasing proportionally to each other, there's not going to be a change in the slope. And so that's why for uncompetitive inhibition, that indicative, the classical indicator of uncompetitive inhibition are these parallel lines moving up the y-axis. And then the last one is mixed, and mixed is funny. And oftentimes you'll hear it called either uncompetitive or mixed, based on what happens to the Km. But we were simplifying it for this class, and we're just going to say it's all mixed. It's not necessarily accurate, but this is the most difficult of the inhibitors to wrap your head around, and for good reason. So what happens with mixed is that mixed can either act either like a competitive or an uncompetitive inhibitor, which is why we call it mixed. And so in both of these, so what happens is that the enzyme, the inhibitor can either bind to the enzyme alone, or it can bind to the enzyme substrate complex. And so in this case, either way, when the inhibitor binds, when the enzyme binds to the when the inhibitor binds to the enzyme alone, oh, okay, let's see here. So it can either bind to the enzyme before or after the substrate. But either way, when the inhibitor binds, it's going to change. It's going to alter the enzyme in some way, shape, or form. So it's going to lower the Vmax of the reaction. It's going to make the enzyme less slower, less efficient in terms of its Vmax. But the Km can either increase or decrease depending on which step it's affecting. So if it's binding to the enzyme alone, if it's competing with the inhibitor, with the substrate to bind to the active site, we could see how the Km might increase. But if it's going to increase to the enzyme after the substrate binds, we could see how it would decrease the Km. And so again, this is rarely seen, because usually it would make sense. Nature is really lazy, and so nature designs itself so it has to exert minimal effort. So it makes sense that that an inhibitor would favor one or the other rather than both. Okay, and so the hallmark, or the Lineweaver-Burke plot, the hallmark Lineweaver-Burke plot for this mode of inhibition is that the lines are going to intersect because the Vmax is decreasing, is changing, but they're going to because both the Vmax of the enzyme, so the y-intercept, and the slope is changing, because both of those are changing, the lines are going to intersect, but they're not going to intersect on the y-axis. They're going to intersect to the left or to the right of the x-axis. So, yeah. Okay. Alrighty. Questions on inhibitors? I feel like I did a better job talking about mix this time than I did the first time, but I guess that's just natural. Yes, Roshan. Okay, sure. Okay. Let's just carve my ink. Okay. All right. So you're asking me, okay, so if we draw out an enzyme plot, VO substrate. So we'll just say, okay, so here's an enzyme. Is this enzyme an allosteric enzyme? Probably not. I guess I drew it a little bit wonky, so maybe you think it could be, but that's a hyperbolic curve. Okay, right. So you're asking which direction would it shift for the Km to increase and which direction would it shift for the Km to decrease? Okay, all right. So if we have substrate concentration, okay, all right. So let's say we're shifting to the right. Okay, so let's say, so if this is our VO, oops, we want to make that V, we want to make our V, not our V, yeah, we want to make it the same. Okay, so if that's our Vmax, 1/2 Vmax is here. Okay, so let's extrapolate over to enzyme alone, and then to enzyme plus inhibitor. So this is the concentration of substrate of enzyme alone, and this is the concentration of enzyme plus inhibitor. Okay, so remind us again, what is Km? Okay, so the Km is the concentration of substrate at which we reach 1/2 of Vmax. So which of these enzymes, so if we extrapolate down to concentration, which of these is a larger, so this is substrate concentration, which of these has a larger substrate concentration on their x-axis at 1/2 Vmax? Which of those is larger? Pardon? Yes. So the one with inhibitor. So if we have, so this has a larger value of value for the substrate concentration at which we reach 1/2 Vmax. So if we shift to the right, that means a bigger Km. Consequently, if we shift to the left, we're going to be decreasing the Km. And it's the exact same thing for the Kd if we're talking just about binding. So you could, pardon? Yes, or that would be would probably be a. So if we were to shift it to the left, the curve would probably have to go down in intensity, because for the other two types, it's not a perfect, I want to say yes, but it's not a perfect comparison because for the other two, the Vmax is going to decrease. So it would be accurate if I drew the curve on the left like this. Yeah, that could be non-competitive. Yeah, non-competitive. Or maybe mixed. But probably going to be non-competitive. And so for something to be mixed, like you're really going to, yeah. It's fine. Right. Yeah, with non-competitive or with mixed, like if the enzyme velocity if the Vmax decreases and the Km increases, it's pretty obvious that it's going to be mixed. Things get a little hairier if the Vmax and the Km both decrease, because then it looks like a non-competitive inhibitor. But in that case, I would say for the case of this class, Occam's razor would apply, where the simplest explanation is the answer in that case. But also if somebody was like, oh, it could be mixed or non-competitive, I don't know which, I would also probably expect that too. But yeah, okay. I'm gonna stop jabbering. Okay, all right. Next. Yeah, sure. Yes.
Are there certain scenarios where like one would be better than the other? Because I know at least for the one in class talking about how the Michaelis Menten hit the data actively because the wrong data point was able to kind of
Yeah.
it. But are there any other situations kind of similar to that?
So if I'm asking you the question of are these data good, like, or is this fit good? If Lyman-Ruberg is not a good fit, I'm gonna make it pretty obvious, like I did in class, because I don't want you wasting time squinting at a data point, being like, oh, is that a good fit? Like, again, Occam's razor is gonna apply. Which, and I actually had that problem in class where one time where I was making up this data set and I was like trying to show that Lyman-Ruberg was bad, and then the data looked fine, and I had to kind of change and be like, well, in some situations. But generally speaking, like, so the Michaelis-Menten fit is always going to be the best fit. And as a researcher, if you're at a university, you're generally going to have access to good curve fitting software. So here, the only reason why I had you do Excel instead of downloading SigmaPlot free from the university and using it is because SigmaPlot only works on PCs, not Macs, and people were having trouble downloading it, and so I just didn't want to deal with that. And I'm pretty sure in Dr. blanking on her name, I'm seeing her face. Dr. Arnett's class, I think they may use SigmaPlot, and I think you do a hyperbolic fit. A hyperbolic fit is generally speaking always best. Like, it's always best to do it's best to do a hyperbolic fit, just generally speaking. But a Lyman-Ruberg plot is a way to go if you don't have access to like fancy graphing software. So for us, I'm talking about the hyperbolic fit, but in our class, you're going to be using a Lyman-Ruberg because you're going to have to make it into a line because you don't have SigmaPlot on your computer. least that I know of. But practically speaking, other when you don't have access to a computer, situations where Langley-Verberg will be appropriate are situations where, like, let's say you're working in the lab, you do your experiment, and for some reason, you have to stop after a certain number of points. Like, you're saturating the signal of the detector, or you run out of enzyme, or a fire drill goes off, and the fire alarm goes off in the middle of your experiments, and you have to drop everything, and you can't pick it back up. And so there's situations where you end up where if you do a direct plot of your data, there's situations where you look at your data and they look like that, and they're not saturating. Practically speaking, that's generally when you would use a Langley-Verberg. So in the long term, I'd still be like, lower your enzyme concentration or just redo it. But if you want to get an answer and you have basically an incomplete set where you can't saturate your data, that's when it would be appropriate to linearize it and do a linear fit. So it would be a combination of looking at the R-squared, because you can have something that's a good fit. Like, if you can have data that look kind of messy, but it's still a linear fit and have like a lower R-squared, but it would still be appropriate. But it would be a combination, I would say, of the R-squared and also just using your common sense to look at the data points. Again, if it's not a good fit, I'm going to try to make it obvious that it's not a good fit. You look at your data points and they're in a line and the line goes through all the points, like, I mean, yeah. So, but I'm not trying to, when I'm doing this, I'm not trying to trick you. I'm not trying to trick you. I'm not trying to trip you up. I don't know. Based on some of my true-false questions on the exam, you may think I am. I don't know. I'm not. I want to make it fairly, I want to make it, I've been in the trap where I've tried to make it obvious and it's not obvious and then we all just get confused. That's not my goal. But yeah, it's really just looking and using the Snicker test. Do you laugh at that graph? If you laugh at that linear fit, it's probably not appropriate. Like, I feel like when I was walking through the room in class, everyone, like, people were, I don't know if they were like snickering, but they were like scratching their heads, and I saw people trying to remove the point. If you find yourself doing that, not a good fit. All right, you heading out, Paige? All right, see you tomorrow. Okay, next. Whew. Okay. Do you guys have more questions? Do you want me to walk over things? Do you want me to give you a minute to process? Okay, I'm going to give you a minute to process. I'm going to go heat up my dinner. I'm going to pause this. I think that's kosher. I think actually it was what I was going to suggest. Let's go over the different assumptions.
It's not moving. Stuff is always moving, but it's not changing one side.
That's exactly, it's not equilibrium. So the pump is adapting the rates of the in and the out, so the concentration stays. So it's adapting the rates, so the concentration, it's constantly trying to replenish the concentrations they should be on either side of the cell membrane.
So is it the rate?
Oh, goodness. So for enzyme kinetics, what the steady state means. Okay. We'll take a look at this plot. Okay, so the first thing is it says assumption 1 system is equilibrium. So when I made this PowerPoint, I used the PowerPoint from another professor who I respect very much. And I watched that professor's videos and they explained it right. I somehow don't always explain it quite right. But it's not so much that the system is at equilibrium, because we're not assuming equilibrium. This is steady state. And as we're going to talk about when we talk about metabolism, equilibrium and steady state are very different. It's that the first step is at equilibrium. So the first step, the substrate's popping on, popping off, popping on, popping off, popping on, popping off. And then periodically, one of those substrates that pops in to the enzyme pocket, it's going to get turned into product before it can pop back off. And the rate determining step, when we're doing Michaelis-Menten kinetics, not for all enzymes, the chemistry isn't some aspect of the chemistry isn't the rate determining step. But in order for us to apply Michaelis-Mentens, we have to assume that it is. Some part of K2 is going to be rate limiting. Whether it's the chemistry or the product coming out of the active site, one of those aspects of K2 is going to be rate limiting. And then if we remember our rate law here.
That means that like you were saying, the enzyme and substrate are like on and off, and that's going to happen anyway, but occasionally it's going to actually go to product.
Mm-hmm.
Okay.
And I have an activity to demonstrate that, which is pretty good if you work out the math. And last semester I didn't work out the math, and Kevin worked out the math for me, and I have since forgotten. I should have taken a picture of it with my cell phone. But it doesn't lend itself well to tables. It lends itself really well to rows because you need groups of 3. But what this activity demonstrates is you have one person, is you have 3 piles of M&Ms representing the enzyme plus the substrate, the enzyme substrate complex, and then the enzyme plus the product. And you give people rates, so they're like every 3 seconds, you move one from the substrate into the ES. Every 2 seconds, ES moves one back. And then every 1 second, or whatever, 4 seconds, something like that, the enzyme substrate gets moved into the product. And what you show is that in each point in time, if you take like a snap, if you count the M&Ms, after like a minute, 2 minute, 5 minute, whatever, the ES in the center doesn't change. So we assume it's at equilibrium. And then one of the ramifications of this is that the concentration of the enzyme of the ES complex at any given point in time is equal to the rate at which it's made, which is the rate const K1 times the EMES concentration, minus the rates or the steps that take away the ES, which is K minus 1 takes away ES, and then K2 also takes away ES. And so we want and for this to work out, that's our slow step. But this is really here to illustrate, to segue into the second point, which is we're assuming the steady state. And so this is a graph. I love showing this graph. And this is the graph that I show when I talk about my research, which is on pre-steady state kinetics, not steady state kinetics. So if we're going to track the concentration of all of the different components of the reaction as a function of time, the substrate is going to decrease with time because you're consuming substrate. The product is going to increase with time because the enzyme is producing product. However, what's going to happen is if we look at what happens to the ES and the total and the enzyme without substrate initially, the amount of enzyme without substrate is very sharply going to drop off, and the concentration of ES is going to sharply increase until it eventually flattens out. And so the steady state assumption has to do with the fact that ES is flattening out and staying constant. So what this means is that in this particular part of the curve where we're increasing, the enzyme and substrate are still finding each other. And so we still have to think about, so in this particular slide, we said that K2, the chemistry is rate determining. But when we're at this step of the reaction, we still have to factor in the substrate and the enzyme finding each other. But once we're in this gray box, that means that in any given point in time, the same amount of enzyme, the amount of enzyme that's bound to the substrate doesn't change. So I'd like to say, so at one given point, the concentration of enzyme that's in the ES complex stays the same. So the change in the concentration of ES with time is equal to 0. And in fact, if you're at a concentration of substrate where you're at the V max, when you reach the steady state, all of your enzyme is going to be I use that liberally, but at any given point in time, all of your enzymes is going to be bound to substrate. And so when the chemistry happens, a substrate is nearby and immediately ready to pop into the pocket and take its place and to continue doing chemistry.
So while this is happening, producing product and using substrate.
Yep. Because you're literally swapping them out.
The slopes would be the same.
And so different enzyme assays can do both. So lactodehydrogenase, which is used in 371L, uses NADH and NAD+. NADH absorbs at 340, NAD+ does not. So depending on which side of the reaction, you'll either watch production of NADH or depletion of NADH, depending on the reaction. And like you would literally, if you had a negative slope, you would literally just take out the negative. No, hemoglobin. Hemoglobin. Yep. We start at hemoglobin. Right. Yeah, those are the big things. And another thing that's really important here is in order for this to be true, the substrate concentration has to be much, much greater than the enzyme concentration. Because you want it, first things first, you want to saturate the enzyme. You want to make sure all the enzymes in the ES, and you don't want the reaction rate, to have any component of the substrate wandering over to the enzyme. And to accomplish that, you have to have much more substrate than you do enzyme. Right. Yep. And again, the Michaelis-Menten equation, this is just distinguishing Kn from Kd, and that when you're looking at a binding protein, you're looking at the Kd, you're graphing the number of sites bound against the concentration. For the Michaelis-Menten equation, you're looking at the velocity of the reaction against the substrate concentration. So you're not just thinking about binding, you're thinking about binding that leads to productive chemistry. Now, because you're graphing the velocity of the reaction against the substrate, you're like filtering out non-productive chemistry. That's just an important, and some people have really struggled to wrap their heads around that, and it's complicated, but I just want to make that distinction. It's there. All right. Yep. This just talks about how the enzyme rate is dependent on the substrate concentration, and the enzyme rate will increase with increasing substrate concentration until you reach a really high substrate. And once you have enough substrate, it doesn't matter how much there is anymore, and that's why the curve flattens out. Because you reach a point where at any given point in time, all of your enzyme is bound to substrate. And then once the substrate gets turned over, the next substrate just hops right in. So you're effectively never seeing enzyme alone. And that's what happens when you reach the top part, or the Vmax of the saturation curve. Yeah. Smaller Kn, enzyme likes the substrate better. Another important thing to note, again, is that the Km is an inherent property of the enzyme substrate pair. And what the Km can tell us how much the enzyme likes the substrate. So if we look at hexokinase, hexokinase has a much lower Km for glucose than it does ATP or fructose, because glucose is its native substrate. And so it can bind and turn over these other things, but it's not going to bind them as well. Oh, hexokinase actually uses ATP. ATP is a substrate, but fructose is not a native substrate. So that's why fructose is going to be lower and a couple orders of higher, or a couple orders of magnitude higher than glucose. Because it can still act on fructose, it just doesn't do as good of a job. It doesn't like it as much. So you'll see a bigger Km. Just run. Yep. Do we talk about the catalytic constant with you, Noah? You were here. Okay. Are you feeling good about it, or do you want to talk about more? Okay. So there was a problem, I think, in one of the pre-assignments. And so you would use the catalytic constant if you're taking two different enzymes and you want to figure out which one is better. Which one's a more efficient enzyme, which is the better enzyme. And so this would especially be relevant, like if you had two enzymes that worked on the same substrate, or if you had one enzyme with two different substrates, and you would want to figure out which one's better. You could use the catalytic efficiency.
So what is the value of it? But by itself, is it really
So by itself, like if you work with enzymes, like you can figure out what's a pretty good benchmark for what makes a good enzyme, like what's the rate enhancement versus the normal. And like and one thing is that like if you get a catalytic constant of like 10 to the 8 to 10 to the 9th, that's your way that you know that diffusion, not the chemistry or the enzyme, is the rate determining factor here. So I think that's like an upper ceiling of what you would see for an efficiency. But I wouldn't expect you to like calculate a catalytic efficiency. I'd just be like, tell me if that's a good catalytic efficiency. Like, I mean, so like it would probably be good to know that for a diffusion limited enzyme, the upper limit's 10 to the 8th to 10 to the 9th, right? But I'm not going to be like, this enzyme has an efficiency of 1 times 10 to the 5th. Is it a good enzyme? I'm going to try to give you something to like apply to. I'm concerned about applying skills, and so certainly you could see some situations where usually unless if we're talking about diffusion, it's probably going to be a case where you're going to be comparing enzymes. Any other questions? Questions, comments, concerns?
It's like related to this, but I guess it could be applied to other stuff. It's like, so we want to draw the active site of this specific thing, whereas the cysteine protease, how, like in relation to the one that we did in class with the trypsin, like comparatively, and like applying that to a different situation with the cysteine protease rather than the serine protease. Drawing the active site, that's something. I'm trying to ask a question, I'm not specifically asking about the quiz, even though that's kind of what I would be applying it to.
Why don't you ask me the question that you want to ask me, and I'll answer it in the way that I want to answer it. Okay. All right. So what you're going to do is you have certain amino acids for papain. Okay. What you have to do is you have to take the two examples that you have, and you have to figure out which one is it going to look like more. But you have two frames of reference for enzyme mechanisms. You have a serine protease and you have an aspartate protease. And so based on what you know about the active site of papain, you have to figure out which one is going to look more like and then adapt the mechanism to the active site that you're given. You have to make a prediction based off the amino acids you have available and the mechanisms that you know about to make a choice. And then a lot of people ask me, do I have to write the substrate in the active site? I would say, yeah. So honestly, for that first step, for that first question where you're drawing the active site, you're really just drawing the first step of the reaction.
Okay.
Yeah, but yeah, and I feel like I've been pretty clear of the fact that you have two mechanisms in your toolkit. I'm not going to expect you to pull a mechanism out of your butt.
What was that?
HIV protease. Yeah. The HIV protease is the one that has two aspartates, and then the serine protease has the catalytic. So it has a catalytic dyad, and then the serine protease has a catalytic triad. Yeah. Alrighty. Rashawn, Rupert, any questions? You waiting for me to come up with things or waiting for Noah to? Trying to think through it, yeah. Yeah, I know. I'm trying to be helpful, but without being too helpful. Without conferring an unfair advantage or giving away the answer. So, yeah. People especially get mad if they can't come to a problem session because they have to work. And I'm like, I'm sorry. Yeah, anyway. Last semester I tried to make all my problem sessions on the same date, and that wasn't always great for people. Okay. All right.
Okay, so yeah, I have another question before you say.
Yeah, sure. Yes.
So you mentioned how in part A we should draw the active site and we should also just draw the substrate as well.
Yeah.
Let's say that like the substrate, there's like a specific substrate, but like
No.
the question there's like a broad, yeah. Right.
So I'm totally okay with you drawing a generic substrate.
Okay.
I'm more focused on you, especially because it supposedly has such a broad specificity. Like, so based off of the mechanisms that we've done in class, like you can have an idea of what the substrate should look like. But I'm not going to be hung up on you having, for you to figure out what the substrate would look like, you might have to like go on the internet and Google it and stuff, and you can't use the internet. So you've got to answer what you can within the constraints of not having access to the internet and just off of what I give you. Basically, like if it was an exam. Except you can hunt through your notes. But you can't for the exam. Sorry. Yeah, so chymotrypsin, if we look at the picture, yeah, okay. So, yeah, that does get confusing because everything is a protein, right? So in this case, and perhaps I should have drawn it like a squiggle, but in this case, the catalytic triad, the catalytic triad are part of the enzyme. So those are amino acids that are stuck in the enzyme, and so like at the beginning they look this way, and then that way at the end they look exactly the same because they're ready to do another round of the reaction. The substrate is this generic peptide here. And so also the phenylalanine binding pocket and the oxyanion hull, those are also part of the enzyme. And they are ways that the enzyme uses to proximity and orient, and then to stabilize the transition state for the oxyanion hull. Over there. Okay, so oxyanion hull is stabilizing our transition state, and the phenylalanine binding pocket is binding and orienting our substrate. But yeah, so the catalytic triad are part of the enzyme. The peptide is the substrate. And then similarly, if we were to, it's not working. Damn it. If you were to look at the mechanism for HIV protease, the two aspartates, and in the book, I feel like the picture of aspartate protease, of the HIV protease that comes from the book, does a good job of showing that that the aspartates or the catalytic dyad are part of the enzyme, and then the peptide, which has a phenylalanine and a proline, that's the substrate. So yeah, so for HIV protease, it's a very specific peptide sequence that it recognizes, and then chymotrypsin, it's just phenylalanines. But you weren't really given a specific substrate for the for papain.
Okay.
Yeah, you weren't really given a specific one. No. Yeah, and again, I'm really concerned about you applying the mechanism. So I'm not so worried about that. You already took a quiz on amino acids, so and peptides. So yeah. Although you certainly shouldn't, you wouldn't want to throw away those skills for subsequent exams. You don't want to forget those. Those are still important, but alas, our priorities have shifted a little bit.
On that note, we can see stuff in the first part of the class, other than like obviously our European last.
So yes and no. So I would say that like it's going to be building knowledge. So you're not going to see like questions like you may see facets of questions that require knowledge from exam 1. Because I feel like exam 1 is foundational for the rest of the semester. So like in order to understand enzymes and binding proteins, you have to understand protein structure. To understand mechanisms, you have to understand whether or not the amino acids can be protonated or deprotonated. That depends on its pKa. And to know about the charge, you also have to understand something about the protonation state. So I would say you'll still have to use the knowledge, but it's going to be more focused on applying those skills to more complex problems. If that makes sense. But it's not like some classes where the parts are distinct and you can just shut off the first third of the semester, but that's not the way this class is. And I try to write questions and have questions in class where we activate that knowledge so you don't lose practice, if that makes sense. But yeah. Yeah, definitely. So like for papain, like again, if you look at the practice exam, you look at the practice exam. There's 2 cases of where you're gonna have to pull amino acids out of thin air. You might want to remember your amino acids for this quiz. Yeah.
Also, you also mentioned classes.
Yes. Strategies. Yeah.
How would you ask questions like we have a class or like classes?
Yeah, that's definitely fair game. So I would try to give you information where you could answer it. So like identifying the class of this enzyme mechanism would be a fair game. Identifying the catalytic strategies that chymotrypsin. Yes. Okay. So I was gonna say, I'm trying to think of a good analogy here. But the class is what is the end game of the mechanism. So in the case of chymotrypsin, what happens if you compare the substrate, it's like if you look, okay. Oh gosh, no, I don't want to bring thermodynamics into it because that'll just be more confusing. With the class, you look at the substrate and you look at the product and you go, what happened? And in this case, it's a bond gets broken and water gets added across it. So it's a hydrolase. Catalytic strategies is what are the toolboxes that the enzyme uses in its reaction. So for a lot of these, you'd have to know the mechanism, right? So in this case, you could go and it's an automatic given that, it's going to use proximity and orientation and transition state stabilization. But you have 2 specific examples of here that if you were asked, you could point them out. Be like chymotrypsin has a phenylalanine binding pocket, and it has an oxygen and a hole to stabilize the transition state. Like there's 2 concrete examples here for you to pull upon. They're not the only ones, but they're there. But also, histidine acts as a general acid and a general base. And then we also see that the enzyme is covalently bound to the substrate at some point. So that would be covalent catalysis as a method, as a strategy. So I like to think of the as the class as what's the goal the enzyme is accomplishing, and the catalytic strategies are what are the tools that it uses to get there. Yeah.
And you want to know, I guess, like to the T of amateur stuff and the
Yeah. Yeah. Fortunately, they're similar. If you know the mechanism of chymotrypsin, you can figure out the mechanism of HB protease. Because it's the same arrow pushing. It's just you have different amino acids that are doing it. And it's the second half of the chymotrypsin reaction.
Why this?
Honestly, because those are the two. So there are two of the mechanisms that are in the book, and there are two that I like the best. And I figured two is a good starting point. Chymotrypsin is really good because it shows all of these different steps. And then I like HIV protease because it's clinically relevant. So, and it also illustrates the point that the identity of the amino acids matters for the catalytic strategies. So again, with aspartate, you're not going to see, at least not in this case, you're not going to see aspartate making a nucleophilic attack. Doesn't mean it can't, but if you've got a peptide, if you've got it sticking onto a peptide, there's a lot of angles stuff going on there, and so you're not going to see an aspartate making a nucleophilic attack. And those are the kinds of thoughts I want you to be having when you're going through with these problems. Is you're looking at the amino acids, you're thinking about it based on what I know from the mechanisms and the catalytic triad and dyad I know. How would this new enzyme fit in between those two? Oh goodness.
As for like little structural combinations or whatever, like the oxyanion hold one of them, phenol binding pockets another one of them. Are there any other ones like that?
Yeah, sure. So I was gonna say that they're out there. I just don't know if we'll see any specific examples quite yet. But I think these are the examples that we have. So if we were to look at, is my PowerPoint working again? Oh goodness, it's a lot. Let's see, enzyme mechanisms. If we look at enzyme mechanisms, okay. So if you look at enzyme mechanisms, if we look at HIV protease, that's the other enzyme we have right now. So if we look at HIV protease, aspartate, goodness. So in this place, the aspartate on the right-hand side is acting as a general acid or base. But what's the aspartate on the left doing? So it is not. So those dash bonds mean hydrogen bonding. So aspartate 25, that's the difference between, one of the main differences between HIV protease and chymotrypsin is that HIV protease literally looks like the second half of the chymotrypsin mechanism, and that aspartate 25 is playing the role of histidine. And then this aspartate 25 on the left is basically acting like an oxyanion hole because it's hydrogen bonding with the O-. So there's something about the conformation of the tetrahedral carbon intermediate that like puts the O- in line with the aspartate 25 on the left-hand side so it can hydrogen bond. So that would be like another example, I would say, of transition state stabilization. All right, so if we go, good old Google. All right, if we look up the oxyanion hull of chymotrypsin. All right, so what's happening here is, in this case, it has the double bonded O there, but it's going to preferentially interact with the single bonded oxygen with a negative charge, and that you have these two amino acids, glycine 193 and serine 195. They're far away in they're on the other side of the active site from the catalytic triad, and what they do is they orient their backbone nitrogen protons so they can hydrogen bond with the oxyanion in the tetrahedral carbon intermediate. So they're literally arranging their backbones so they can facilitate the formation of the O-. Because again, peptides can break with time and eventually they'll degrade. It's just going to happen really slowly. And so with transition states, in this case, putting these hydrogens in a spot where they can hydrogen bond with the transition state lowers the energy of the transition state, which means that the activation energy is smaller, activation free energy is smaller, and so the reaction can be sped up compared to like if you just have a peptide sitting on its own hanging out in water with no enzyme around. Yeah, so the protein can orient different side chains or its backbone, uncertain amino acids that are close in space, that can make it easier for the transition state to form, therefore speeding up the reaction. That's the oxyanion hull.
Where does that at?
So it's happening the whole time. It's just I drew it in on the first step. It doesn't go away. It's just I didn't want to draw in oxyanion hull like for every single step. I just drew it in once.
And is that where the aspartate has that bond with the hydrogen?
So in that case, that's something different. So that is the aspartate. So that's the aspartate pulling on the nitrogen to make it, pulling on the proton and the nitrogen to make the histidine more acidic, so it can more easily abstract the proton from serine. So serine normally has a pKa of 13, which is why we didn't memorize a pKa for it. But there are certain amino acids in the environment that lower its pKa to 7 in chymotrypsin, and one of those factors is the fact that you have the histidine being more acidic or basic than normal, and so it can more easily abstract and pull out that proton. That definitely is important and plays a role. All right. I'm tired, guys. But I've already said that. I know you guys are tired too. I've got to run back to downtown before I go home because I realized I left out. So it's in bottles with caps, but I definitely left out some organic solvent. So I need to go put those. I need to go put those in waste. I need to go put those in waste, really quite badly. So, all right. Well, thanks for coming out. I'll see you guys tomorrow. Do you have any other questions, Noah? I see you're still here to be puzzling. You've got another 5 minutes of my time if you want to take it. Okay. Well, if you're feeling good, that's awesome. See you tomorrow, Rajan. Okay, good. I'm glad. Again, I really don't like doing these things the day before a deadline, but consistently most people are available on Wednesday. So consistently most people are available on Wednesday. And if I do it when most people are available, you can't claim I'm paying favorites or something. So yeah, it's just easier that way. Alrighty.
Chunky was